welcome back. We are going to do 2D velocity vectors again. So let's do relative velocity in 2D. I'm doing one of the questions from the class test because I've been specifically requested. I've put the test question in the description of the video, so please just refer to that if you are not sure what the question is. Okay, so part of the question is we are first told that there are two airplanes. We've got airplane M, and I'm going to say that we've got the velocity of M relative to, you can say the air or the earth, I'm just going to say the earth. Velocity of M relative to the earth is 200 kilometers west, and the velocity of N relative to the earth is 250 kilometers south, and we need to know what the velocity of M relative to N is. Okay, right, so that's our basic information that we need. We're also told that we need to do a scale diagram. Now, of course, if you're doing a scale diagram, I want to see this, and I want to see a ruler straight away. You can have the long ruler, the short ruler, it just depends on how long the actual line you need to do is. If it is a long line, please use a long ruler, not two rulers sort of end to end, because it is just not going to work. Okay, so we've got a ruler, we've got a protractor, perfect. And let's have our normal little compass that we always use, because I can never remember directions without a compass. Great. Now, even though you're doing a diagram, we still need to have your basic equation so that your diagram is drawn correctly. So I'm just going with my normal sandwich method. So we need to know that velocity of mn is equal to velocity of m plus velocity of something n. So remember our little sandwich, there we go. And to complete our sandwich, we put velocity of, put the relative, sorry, what was that, door? Put our frame of reference as our sandwich. Now, do we actually have all of these? We've got this one is here, but we do not have the velocity of Earth relative to n. We do, however, have the velocity of n relative to the Earth. So what do? We just invert it. Now, because this is south, we can just invert it straight away, easy peasy. We can say that the velocity of E relative to the n, you don't have to write this down, I'm just writing this for clarity, is 250, magnitude is the same, kilometers per hour, north. Because it's inverted, it's directly opposite. The magnitude is the same, but the direction has swapped. Now, there's two ways of doing it. I like the sandwich method, it's consistent. You just need to be able to invert your direction, but there is another way of doing it. If anyone would like to know it, just let me know, I'll do another video. Great. Okay, so now we've got our little equation. Now we can actually draw. Can we draw? No, we need to know our scale. So the question specifically tells us our scale. 1 centimeter is equal to 25 kilometers per hour. Okay, we're told that. If they don't tell you, you have to write your own scale, and you have to write it down like this. You could make, like I said, make your own scale, but write it down. So 200 divided by 25 is 8. That's 8 centimeters. And 250 divided by 25 is 10 centimeters. Okay, so we know how long our things need to be. Is this ruler long enough? Does it have an 8 and a 10 on it? Yeah, so the short one's perfectly fine. So first of all, velocity of m relative to the Earth is straightforward, it's west. So which way is west? That way on our piece of paper. And that is how many centimeters? 8. Perfect. So take your sharp pencil, not pen, I just use pen for the video, but please use a pencil. And there is our one vector. Now, because we're adding it to the other vector, we need head to tail. So the other vector is, was this 8? The other one is Now, because we're doing Earth relative to n, it is north. So we need 10 centimeters north. Now, don't be a nana like I have been and have your vector so close to your writing that it all collides. But that's just how it's ended up. Okay, so we've got our two vectors. What do? Easy peasy. We just join them with our pencil, not with the color I'm about to use. No, we don't do that. What do? We label. We label. So this is velocity of m relative to e, which is 200 kilometers per hour. And this is velocity of e relative to n, which is 250 kilometers per hour. Right? Always got a label, otherwise what are you doing? We don't know, you're just drawing a round triangle. No, not great. Okay, then we join our triangle nicely with your nice sharp pencil. Okay, and super simple. You can actually use this method to solve any vector diagram. You just have to be accurate. That's the only difference, is accuracy is important. Okay, so that this length is 12.7 centimeters. And which is this? This is the velocity of m relative to n. What is 12.7 centimeters, you ask? We have to times that by 25 to find our speed, because that's actually what we're asking. Are we asking how long the line is? No, we're asking how long the speed is. So 12.7 times 25 is 317.5 kilometers per hour. Okay, how many significant figures? Okay, it looks like we've only got 2. You could have 2 or 3, depends, but I'm going to go with 2. So it's 320 kilometers per hour. Are we finished? No, of course not. We need our direction. Now that's what our protractor does. So that looks to me like, now of course your accuracy will depend on your drawing. So to me that looks like 50 degrees, this angle here. It looks like 50 degrees. 50 degrees what? Again, this relates to the question, does this ask for a bearing or does it ask for direction? If it asks for direction, your two options would be 50 degrees north of west, or of course the correlation, 40 degrees west of north. All right. Le vin.